Hi, welcome to another lesson at EDU Solutions Institute. Now, today we're going to continue on our IB physics syllabus talking about rotational objects. Because the last week's lesson we focused on angular velocity, angular speed, angular displacement. Now, this week we're going to use that principle to help us to look at angular momentum, and we talk about the energy that objects have rotating or sliding. So stay tuned as we explore more on the IB physics syllabus. Now, what do we mean by angular momentum? Because angular momentum is somehow similar to what we know before, which is linear momentum. And linear momentum had to do with objects, the effect of objects moving in a singular plane. So therefore, if we look at the x-plane or the y-plane or the z-plane, these are the effects that objects have moving in these unique planes. Now, if we go now and explore what is angular momentum, then angular momentum is the same effect of objects moving, but this time it is moving in an angular motion, which means it's moving in a circular motion. It's either rotating, it's either sliding, or it's either making a circle. So that's what angular momentum has to do with. And more specific, it has to do with the product of getting the angular velocity and or moments of inertia. Now we get that L, which is angular momentum, will be equal to I, which is the moment of inertia, times sigma, which is your angular velocity. And hence from here we know that the SI unit of angular momentum is kilogram meter squared, which is the unit for moment of inertia, rad per second, which is the unit of angular velocity. Now, just like linear momentum, there has to be a conservation of angular momentum as well. And the conservation of angular momentum tells us that if we have an object rotating or spinning, right, and then we change the mass of it, either we add some mass to it or we remove some mass from it while it's still rotating, with angular momentum, the conservation that if we add something to an object that's continuously rotating, then the momentum of this rotational object will be conserved. And therefore, we have that the sum of angular momentum before would be equal to the sum of the angular momentum after. So if we can imagine a spinning disk, and then as it's spinning, we add a little mass to that spinning. Therefore, without the external forces, any external forces acting on that spinning disk, then when we add that mass to it, the momentum of the angular rotation will be conserved. And that's what this relationship tells us. Now, objects rotating definitely has to do with energy, conservation of energy, right? And because it's moving, then we have kinetic energy, because kinetic energy deals with objects that are moving. What's the energy that they have? So we have the rotational kinetic energy, which is equal to half times the moment of inertia times omega squared. And omega squared here represents our angular velocity or angular speed, and I represents your moment of inertia. Right? So therefore, if we take an object, for example, a wheel that is rotating about its center, right? So here we have R being its radius. So if it rotates or it's rolling on this surface, right? If it's rolling in that way, so that is its angular velocity. Then what we do is that if we take a point on the object to be here, right, this point would be a height above the ground, right? So here we have, this is your height from the point where it's starting, right? So therefore that height represents here. So what we know is that before the object is moving, it has a potential energy at this point. That potential energy, mgh, will be converted into rotational energy, which we'll call your rotational kinetic energy, right? Which is half I omega squared. But because objects in rotation has not just angular momentum, angular speed, it also has linear speed, v. So because it also has linear speed, we also will have a linear kinetic energy rolling with this wheel. So therefore, we will have that the conservation of energy would be that the potential energy of that point at the start would be converted to its angular kinetic energy as well as its linear kinetic energy. Because as we know, this v represents your linear speed, and then we have the mass, which would be the mass of the object that is rolling on the surface. Now, we have described rolling, right? But therefore, sometimes you hear the word slipping. And slipping has to do with when there is no friction on the surface between the object and the surface. So therefore, objects will only slip when there is no frictional force. But once there is frictional force, it's no longer slipping. It is now called rolling, right? So with the absence of the frictional force, then we have slipping or sliding. But if there is frictional force present, then we'll have rolling instead of slipping or sliding. All right. So as you can see, the principle of angular momentum and rolling kinetic energy is the same for linear situations. The only difference, as we see last week, is that we have to consider the unique terms, the unique symbols, and the unique units that we use to represent these specific angular situations. Now, you have read it to the end. I hope you have understand a little bit more about angular momentum as well as the conservation of angular momentum with the use of kinetic energy as well. So that's the end of this video. So please remember to like, subscribe, share with someone that you will see will make benefit of this video. And I'll see you next week where we continue to learn about the IB physics syllabus. Thank you.